So this is what we have at the moment. Let's have a look here in the Pyro solver at the parameters that allow us to control what's happening and how the smoke simulation evolves through time. One thing we can do is here on the combustion tab, we can actually disable the enable combustion because we're not going to be calculating any combustion. And let's go first here to the simulation tab where we have timescale, temperature, diffusion and cooling rate, viscosity and buoyancy. Let's talk about buoyancy first. So as you can see, even though we don't have any velocity in our source, the smoke simulation is actually rising. And the reason why it's rising is because we are adding temperature to the simulation, and the temperature is going to affect the buoyancy of a gas, in this case the smoke. If we lower the value of the buoyancy, you'll notice that we will have the smoke isn't going to go as high as fast. So let's go to put the buoyancy at 0.5, so 10 times lower, and as you can see, it doesn't rise as fast. The direction of the buoyancy can also be controlled. You have a buoyancy direction here. Typically, you will want to maintain the Y direction as being up and as being the direction for the buoyancy, but you can change this to any vector that you might want. Now, you know that the buoyancy works like this. Let's go in the opposite direction. Let's go to 20, and that should make the smoke rise a lot faster, as you can see. Okay, and that's pretty much buoyancy in a nutshell. The other parameters that actually influence and are related to the buoyancy is the temperature, diffusion, and the cooling rate. These two affect how the temperature is actually being calculated and evolving inside the container. We can have a look at that here on, if we go here to the smoke object, on the visualization. Right now we're just having a look at the density, but we can turn that off and turn on the visualization of the temperature. And this is going to give us a black body representation of the evolution of the temperature as we start by adding it here, where we have our source coming in. We add that temperature, and then it rises up with the smoke, and then it starts to dissipate. It starts to cool down and gets colder. Okay. Of course, as you can guess, here on the Pyro solver, if we control the cooling rate, let's say we have a cooling rate that is much slower, 0.01, you'll notice that we'll keep these bright values for much longer. It doesn't cool down as fast. Of course, you can also do the opposite, and if we go to a cooling rate of 5, you'll have something that doesn't really go anywhere because it cools down very, very fast. I'm going to switch this back to the default value. I'm going to use Control and middle mouse button to click on the parameter and switch it automatically to the default value. And let's have a look at the effects of temperature diffusion. So temperature diffusion, as the name implies, has an effect over how the temperature is going to pass on from voxel to voxel. If you have a higher diffusion, that contamination of temperature values to other voxels is going to be higher. You're kind of blurring out the values with a higher diffusion. Let's go to 5. So it's very extreme. It blurs so much that it doesn't have the chance to evolve. And you can go the other way around, where you reduce the temperature diffusion so that it doesn't blur as much, and you should keep more detail. Okay, so temperature diffusion and cooling rate allows you to control the evolution of the temperature, which by itself, which in itself is going to affect the evolution of the density throughout the simulation. Let's just turn this off, turn on the density, and you'll see that we have different types of behaviors. I'm going to reduce the buoyancy a bit, and you should play around with these values until you get something more interesting. Timescale. Timescale is a way of controlling how the evolution of the simulation goes by, the speed at which the evolution of the simulation happens. At 1, it should be the usual, the standard, but you can make things go much slower just by controlling the timescale. it will have an effect over the evolution of everything. Or you can make things happen faster. If you want to break up the simulation a bit more, again, you can continue to reduce here the... Let's have a look at our source. And here we have... Let's make sure we have this a bit more broken up here on the attribute noise. I'm going to make sure we have... we can also play with the distribution here. To cut out a bit more, and maybe play with the size. I'm going to increase the size a bit to 0.5 and then use the roughness 0.8. And this might give us some more interesting shapes. I think we'll have more variation this way. Let's have a look. Yeah, it's a bit more broken up. Okay, so this is our first simulation, and we learn about the most basic parameters to control the behavior of our simulation. Timescale, to control the speed at which the calculations, the speed that are considered when doing the calculations. The temperature diffusion, which influences how the temperature of one voxel passes on to the temperature of the nearby voxels, kind of a blurry effect that you can apply to the temperature. And the cooling rate, which will be the speed at which the temperature is going to cool down. You also have the buoyancy, which controls the speed at which the volume is going to be rising based on the temperature, and you have the buoyancy direction. On the next lesson, we're going to be looking at the microsolvers that come in with the PyroSolver to help us control the shape of the simulation.